Okay, continuing on here with our review problems. We have, looks like a weak acid problem, right? I think we're fair to say we're pretty fond of these now. And in this case, we're told the pH of a 0.040 molar hypobromous acid solution, probably should belong there in the problem, is 5.05. We want to calculate Ka. So a couple things we should know how to do here. HOBr, that's hypobromous acid, that is a weak acid, so it would have this reaction in aqueous solution, right? It's an acid, so it's going to donate a proton to water, which would make hydronium ion, right? And that would leave the conjugate base, which would be hypobromite here. OBr minus, or BRO minus is often how it's written normally. Now, based on that reaction, the equilibrium constant expression would be Ka is the concentration of hydronium times the concentration of the conjugate base, the hypobromite, divided by the concentration of the weak acid. So if we could figure out those concentrations at equilibrium, we can plug them in and solve for K, which is what we're asked for here. Now, the pH does give us some information about what's happening at equilibrium. So we do want an ice chart here. Now I kind of messed up my spacing, but I think you can probably still figure out, right, our ice chart here. Now initially we know our solution is 0.040 molar in the weak acid. And remember, initial conditions are when we haven't moved from that initial solution towards equilibrium yet, so those would both be 0. Now, what we can figure out here, though, from the pH is what the concentration of hydronium ion is once this does reach equilibrium. So we should know that pH is the negative log of the hydronium ion concentration. If I plug in the pH, then I can solve for hydronium ion concentration. So 5.05 would be equal to the negative log of the hydronium ion concentration, right? So if I move this negative over, and then I do the opposite of a base 10 log, which, right, if you look on your calculator and you find the log key, the second function generally is going to be the opposite there, so 10 raised to the x power. So move the negative, and then I'm going to do 10 to the x on both sides, or the anti-base 10 log, and that would give me on this side 10 to the minus 5.05 is equal to the hydronium ion concentration. So 5.05 negative and 10 to the x, that is 8.91 times 10 to the minus 6th molar for this particular problem. So that's the hydronium ion concentration at equilibrium. That can go in right here into my ice chart. Since hydronium is coming from the same reaction as conjugate base, it would also be 8.91 times 10 to the minus 6th at equilibrium. Now, to be complete here, once we know the concentration at equilibrium was a change from 0, so that gives us the plus here for each of those, the change for each of those in the ice chart. Now, back here, the change in how much weak acid reacted would be the same, but it would be in the opposite direction because it's going down, it's lowered. Now, in this case, you might notice that's a really small number, 10 to the minus 6th, compared to 0.04. And that's a small number too, but there's several orders of magnitude different here. So if I take 0.04 and I subtract 8.91 times 10 to the minus 6th, what do I get? 0.03999. So certainly to the two significant figures we have for concentration, this doesn't change. In fact, to three significant figures, we would still round this to 400. If we got to four significant figures, then we could keep 399, but that would still be a very, very tiny change. So we can keep that one the same, right? This would be a case where that minus x would be something we could probably eliminate from our calculation. All right, got all those concentrations at equilibrium. We can just plug into this equilibrium constant expression I mentioned before. So the two on top are the same, so I'm going to write that as a squared instead of writing them out twice. Divide that by 0.040. And that will be our equilibrium constant. So 8.91 times 10 to the minus 6th, square that, divide by 0.04, and this comes out to be 1.98 times 10 to the minus 9th. Now, all the way back to our concentration, we really just have 2 sig figs there, so we should round this to 2 sig figs, and that would make it 2.0 times 10 to the minus 9th. That's our Ka value for this acid. So, pretty weak acid, but that kind of matches with the pH there, 5.05, definitely on the acidic side, but not a real strong acid in this case, although it's a low concentration there as well. Okay, probably worthwhile to think about for this particular type of problem. We could flip this kind of on its ear, and instead of giving you the pH, give you the Ka instead. So if I gave you the concentration and the Ka, it's not that different of a problem. What's different is what you would do with your ice chart. So if you know the initial concentration here, but you don't know the change, and you don't know anything about equilibrium, you'd have to start calling these x. So this would be minus x plus x plus x, and then when you got down to equilibrium, you'd have all of the concentrations in terms of x. That's how you could solve then for x to figure out what the concentrations were at equilibrium, and then generally with a weak acid, you'd take the hydronium ion concentration and use that to figure out the pH of the solution. Okay, so we'll stop there with that one, and I'll jump over to the last page of the review in the next video.